So, any questions from what we were doing last time? Okay, we'll just review briefly what we did. So if you remember, we were looking at you're just looking at this first part of quasi-static flows. Let me just share my screen. So we were looking at how we can study this, and I'm saying quasi-static flows, but it could also be just static flows. Static materials, no flows at all. So they both are dealt with in a similar way, and so we talked about either static particles, like let's say you just have a container full of particles, and then or you have very slow flow, that is your inertial number is much less than 0.1, and in these cases the stress transfer is dominated by interparticle friction. So to do this, again we need some theory to understand this, and instead of looking at particles, we are going to be taking a continuum approach, which means that everything just smooth over, and at every point we can define the stress. And the first thing we want to do is we want to be able to calculate the stress at any point. Now we saw that, and we saw earlier also, that the stress tensor has actually a scalar plus two directions, and those two directions are, one is for the force and one is for the area. And for the area, we decide the direction based on the unit normal vector to the area. So at any given point, we can define one direction for the area and one for the force that is acting. And stress, is just force per unit area. And we saw last time that if we do sigma dot E1, that will give us the force acting on a surface, a force per unit area acting on a surface with a unit normal E1. This term inside the brackets is a vector. And then when we take a dot product of that vector with another unit vector, then this gives us the component of the force in the direction E2. So we get E21. This is the stress, which is equal to force per unit area acting on a surface with a unit normal E1. So this is one direction. The surface has a normal E1 and in the direction E2. So this is the direction of the force. And because these two are orthogonal to each other, this is called a shear stress. And same thing, if we took a dot product with E1, then we'll get sigma 11. And there it is again acting on the same surface, but now the direction of the force is in the direction E1. This is called a normal stress. So sigma 11 is normal stress. This is a shear stress. So if you are given a stress tensor, in general, this will be a matrix of some kind, and 1 could be X, 2 could be Y, 3 could be Z. So in general, you'll have a matrix something like this, and then sigma Yx is the same as XY, sigma YY, sigma YZ. Then again, this is sigma xz, sigma yz, and sigma zz. Sorry, you can't read it very clearly, but you can see that you have this matrix and it is symmetric. So these components are the same as these ones. So there are 6 unknowns in general. And if you look at sigma xx, that is the same as sigma 11, it's the normal stress, sigma yy is the normal stress, sigma zz is the normal stress, and the other 3 are the shear stresses. So now the first thing that we did last time was to say that, okay, supposing I wanted to calculate the stress on any surface which is oriented at some angle alpha to the x-axis. So we define a new coordinate system, x prime, y prime. Vivek.
Sorry, sir. Actually,
No problem. How are you?
I am fine, sir. How are you, sir?
Okay, good, good. We're just reviewing what we are doing, what we did last time. So we just want to know, supposing instead of this coordinate system, in this coordinate system, what would be the stress? So if you want to calculate sigma x prime, so now the unit vector in the direction x prime is n. So you do sigma dot n, and this we saw comes out to be like this. And similarly, we can calculate the shear stress sigma dot n dot t. T is now in the direction y prime, and there we got this. And what we said is that if you change this alpha, the magnitude of these two are going to change, and because of the sine and cosine function, they are going to go up and down. And you can find an angle at which this normal stress will be maximum. And for now, we are looking only at a 2D system. 3D we will see later. So these are so there are only 3 unknowns over here, 3 stress components. I'm sorry, 3 known values, xx, xy and yy. These 3 are given to us. And so if we change alpha, then we can calculate what is the normal stress in the new coordinate system and the shear stress in the new coordinate system. And if you want to calculate what is the angle at which the normal stress is maximum, then that is given by this. So we did all this, and to get this, all we have to do is take a derivative of sigma x prime and put it equal to 0. And then if we substitute for this tan 2 alpha m in this equation and then do a little bit of simplification, then we can get what we call the principal stresses. These are the largest and the smallest normal stresses that you can get in the system, sigma max and sigma min, and that is in terms of the known quantities, sigma xx, sigma yy, and sigma xy. These 3 are known quantities, and here you have plus and minus. So when it is plus, you'll have sigma max, when it's minus, you'll have sigma min. Okay, so this is the thing that we had done, and I think we stopped at this point. Is that right? So we can continue now. From where we left off. So we are today in lecture number 13. And today happens to be 24th of August 2020. And so this is where we had ended last time. Sigma max, comma sigma min. This is what we had got. And today, let me just start with a simple thing. Let's just do an example. So, I'm giving you this. Okay. Now, first, I want you to tell me what is alpha m. Can you calculate that? Or tell me better than that, tell me what is 2 alpha m. Can someone tell me what is it? Anybody?
60.
Correct, correct, perfect. So, the formula is like this. If you remember, tan of 2 alpha m, this we have already calculated in the previous thing. Here is the formula: 2 sigma xy divided by sigma xx minus sigma yy. So we write that down: 2 into sigma xy, that is root 3, divided by sigma xx, that is 3, minus sigma yy. Sigma xx minus yy is 2. So tan of 2 alpha m is square root of 3, and that essentially gives us that 2 alpha m is equal to 60 degrees. You can just put it in your calculator and you'll find out that in fact this is correct. Now let's go to this formula. We'll go to first this formula. We will go to this one. I'm sorry. We will go to this formula. That sigma x prime is this, and then into this into cos 2 alpha, and this into sin 2 alpha. Okay. So we shall write this down, that I'm going to call that as just sigma. That is the normal stress at any angle. So this formula we have already calculated, that if you want to find out at any angle alpha, it's this. So this, if we write down now, substitute for this sigma xx plus sigma yy by 2. This is just equal to 2, 3 plus 1 by 2. Then sigma xx minus sigma yy divided by 2, that is 1. And cos of 60 is what? Does anyone remember?
1 by 2.
1 by 2. So this is 1 by 2 cos of 60 plus sigma xy is root 3, and sine of 60 is just root of 3 divided by 2. So you can see that this is 2 plus 3 by 2 plus half. So if you add it all up, you will get sigma is equal to 4. So at 60 degrees, you get sigma is equal to 4. And if you now go to this formula, so we'll have sigma max is just equal to this value, which we have already got, is 2. And now we're looking at the maximum. So we take plus, and here sigma xx minus sigma yy whole squared, that is 4, my plus. Now you have 4 times sigma xy whole squared is 3 into 4, that is 12. Square root divided by 2. So this is what 12 plus 4 is 16, square root is 4, divided by 2 is 2. So we see that even if we use either of the formulas, we will get sigma max equal to 4. So in this way we are able to calculate this in 2 different ways. Okay. And just now we'll go on to little bit further and look at the thing that I wanted to just say is that all of this stuff that we have done, starting from here, all these things that we have done, this is for any material. It doesn't have to be for a granular material. This, all we are saying is that if you are given a stress tensor, then for any material, you will be able to find an angle at which the normal stress is maximum. And at that angle, actually, if I continue that example, if we want to find out what is sigma x prime y prime at 60 degrees, you will see that it is equal to 0. So what is the formula for sigma x prime y prime? Is here half of sigma yy minus xx into sine of 2 alpha plus sigma xy into cos of 2 alpha. So this is just sigma yy minus sigma xx divided by 2 into sine of 2 alpha. Sine of 60, that turns out to be, I'll write that down for some time. Plus sigma xy into cos of 2 alpha. Correct? This is what the formula is. So this is the formula. So I've written it down correctly. Now let's substitute for these. So we have this is equal to 2 minus 1 divided by 2. So this becomes minus of root 3 by 4. And then here you have plus sigma xy is root 3. This is 3 minus 1, that is, this is root 3 by 2. Let me just do this. 1 minus 3 divided by 2 into root 3 by 2 plus this is root 3 into cos of 60 is just half. Sine of 60 is root 3 by 2. So, okay, so now you will get this is equal to minus of root 3 by 2 plus root 3 by 2, which is equal to 0. So for any material you can show that there will be a certain angle. In this case, the angle is 60, or maybe alpha m is 30 degrees. So at alpha m equal to 30 degrees, your normal stress will be maximum. That is your sigma max. And that in this particular case, it's just 4. And your shear stress will be 0. And this is true for any material. It's nothing to do with with granular materials. The actual thing about particles and granular materials will come a little later when we talk about what happens when, or what will this condition for yield be? That is, what will be the relationship between these two, between the shear stress and the normal stress at the point of yield. That is where the part about granular materials. But here, whether you're looking at a fluid, whether you're looking at a solid, anything, you can always, at a point, you'll find that there is a certain direction in which the normal stress is maximum, another direction where it is minimum, and along those directions, the shear stress will be 0. Okay, so now let's start and do a little bit of new things. So can we find an angle? We found that angle at which the normal stress was maximum. Can we find out what is the maximum shear stress? And for this, what we have to do is take the derivative again, sigma x prime y prime by alpha. We put equal to 0. And now here I've written the formula just here. So when I take the derivative of this with respect to alpha, so then you have sigma yy minus sigma xx divided by 2 into 2 cos of 2 alpha m. I'm going to call it prime because this is the angle at which the shear stress is maximum. Alpha m is the angle at which the normal stress is at maximum. And this will give us minus sigma xy into 2 sine 2 alpha m prime is equal to 0. And so you will get another angle. So tan of 2 alpha m prime is just equal to sigma yy minus sigma xx divided by 2 sigma xy. So you can see that there is a really close relationship between alpha m, tan of 2 alpha m, and tan of 2 alpha m prime. Just to write that down again, for the maximum normal stress, we have tan of 2 alpha m, that is just given by 2 sigma xy into sigma xx minus sigma y. So from these two, so this is for the maximum normal stress, and this is for the maximum shear stress. Okay, just to remind you. But now if you look at this, what will happen if I take tan of 2 alpha m prime multiplied by tan of 2 alpha m? What will I get? What is this equal to?
1. 1.
No, it's not 1. Look carefully.
-1.
Correct.
Minus.
Minus 1. So what happens if these two tans, if the product is -1? That means that the difference between the two angles for the, so if tan theta versus tan alpha times tan beta is equal to -1, that means alpha minus beta is 90 degrees. If they are separated by 90 degrees, then the product of the tangents is -1. So if that is the case, then this implies that the absolute value of 2 alpha m minus 2 alpha m prime is equal to pi by 2 or 90 degrees. That means alpha m minus alpha m prime is equal to pi by 4. So what it says is that if you are looking at let's say the principal axis, then the axis along which sigma or shear stress is maximum are at 45 degrees to the principal axes. Principal axes are those where the normal stresses are maximum. So, you're slowly getting a picture, so that as you rotate the surface, what will happen is that you will come to a particular angle at which your normal stress will be maximum, and along that the shear stress will be 0. Then if you rotate the surface more, then of course your normal stress will decrease, and your shear stress, which is 0, will slowly increase and it will become maximum. And that angle, so between the principal axis and the angle at which shear stress is maximum, is 45 degrees. And then again, if you turn it by another 45 degrees, that means if you turn the principal, you are going at 90 degrees to the principal axis, then again you will have shear stress equal to 0, and your normal stress will be the minimum value. So you go from sigma max to tau max, that is maximum shear stress, to sigma min as you turn by 45 degrees each. Okay, so this is it. So now if you are sort of imagining that I'm rotating all this and the stress is going up and down, that means that perhaps all this can be expressed as a circle. And in fact, quite long back, Moore showed that these stresses can easily be rotated. I mean, these can be easily represented as points on a circle. So he's written that as Moore's circle of stresses. Okay, so that's just a convenient graphical way of representing the stresses. So what we can do is, we have already got this. So I'm going to write this formula again, where we have sigma x prime x prime. I'm going to call that as just sigma, just by the short form. And this we have already seen is just sigma xx plus sigma yy divided by 2 plus sigma xx minus sigma yy divided by 2 into cos of 2 alpha, and then we have plus sigma xy into sine of 2 alpha. So this is what is my normal stress. Now supposing we rewrite this, that is, instead of measuring the angle from the x-axis, let's define a new angle, and I'll call that angle as alpha p, and that let's call it, let's define this as alpha minus alpha m. Okay, So if we imagine that we had our original x-axis and y-axis, and then we we had this surface, and this is now the new x-axis, and this is the new y-axis, where this angle is alpha, and then there was another angle which we call alpha m, at which the normal stress is maximum. And now what we can say is that if we write all our equations in terms of alpha p, so instead of measuring this with respect to x, it is measured, the angle is measured with respect to alpha m. So if you can imagine now that instead of writing this in terms of alpha, I want to write it in terms of alpha p. So all we have to do then is we write alpha p here, but now sigma xx and sigma yy, since at alpha p equal to 0, you are essentially equal, you are along the principal axis. So then sigma xx will be sigma max and sigma yy will be sigma min. So when we write this in terms of the relative to the principal axis, then this just becomes sigma max plus sigma min divided by 2, and this is just and this is cos of 2 alpha. So this is exactly the same as this equation, but now this is written relative to the principal axis. So now here you can see this, that when alpha p is equal to 0, then your sigma is equal to sigma max, and when alpha p is equal to 90, then this is minus 1, so then sigma is equal to sigma min. So this equation is exactly the same thing. All we are doing is we are writing it relative to the principal axis. So we have just defined a new angle here like this, and then so the normal stress is just given by this. You get it? So what we did was essentially we have written everything in such a way that everything is in terms of the maximum and minimum normal stresses, which given any stress tensor, we've seen we can always calculate these sigma max, sigma min, and alpha m. So given any stress tensor, we can easily write this down. And in fact, very often we will redefine these as sigma, just as a short form, as sigma m, which is the mean stress, and this we'll call it as tau max, and we'll show that this is in fact the maximum shear stress times cos of 2 alpha p. So this is the simplest way of writing the stress. So the normal stress, if you can write it in terms of the principal stresses, or like this. So here this term in brackets is tau max, and this term in brackets is sigma m. And then similarly, we can write down our shear stress, sigma x prime y prime. This, you will remember, is just sigma yy minus sigma xx divided by 2 into sine of 2 alpha p, and 2 alpha, not alpha p, plus sigma xy into cos of 2 alpha. Correct? This is what I had written down earlier also. This is it. Sigma yy minus sigma xx divided by 2 into sine of 2 alpha and sigma xy into cos of 2 alpha. This is what I have written down here. So this is when we write it in terms of alpha. Now if we turn it in terms of alpha p, so clearly what we will just get is your sigma xy is just equal to 0 in relative to the normal, relative to the principal axis. So your sigma xy relative to the principal axis, we'll call it as just tau, is equal to just the first term, because the second term will be 0, that is sigma max minus sigma min. There will be minus sign in front, divided by 2 into sine of 2 alpha p, and that's it. And then if you write it in terms of tau max, so you can see why it is tau max. The prefactor is just this. So then tau can be also written as just minus tau max into sine of, where tau max is just this term. So it's the maximum value of tau. So sigma is the normal stress, tau is the shear stress, and alpha p is the angle measured from the principal axis. So when alpha p is equal to 0, you will see that when alpha p is equal to 0, tau is equal to 0, and sigma is equal to sigma max, as what we saw from here. So this is what. So this is just another way of writing it. But once you write it like this, then all of you will understand that I can easily write this in the form of a circle. In fact, these two equations, if you see, they are equations for a circle. So if we look in the tau and sigma plane, then these are parametric equations for a circle, and we can easily see that if we put sigma minus sigma m whole squared, this is just going to be equal to tau max squared into cos squared of 2 alpha p, and tau squared is also equal to just tau max squared into sine squared of 2 alpha p. If you add it up, you simply get sigma minus sigma m whole squared plus tau squared is equal to tau max squared. Okay. So is this an equation for a circle? If this is an equation for the circle, then what is the radius of the circle? Anybody?
Sir, radius of circle will be T max, sir.
Correct, correct. And the center? What will be the coordinates of the center of the circle?
Sigma m comma 0.
Correct. So maybe this is too easy and you can all figure it out. But you know what we can do is we can easily plot now. The axes are sigma and tau. So sigma is the normal stress, tau is the shear stress. And you know, sigma m, this is sigma m, that is the center of the circle. And then you will have a circle like this. This doesn't look like a nice circle. Let me try again. Looks something oblong. Slightly better. Now, this point, as we have seen, this is sigma m, and this radius is tau max. Now, if we go back to these equations, you know, if we go back to this equation and this equation, you can see that sigma is just given by this. So sigma minus sigma m is just tau max cos of 2 alpha p, and tau is equal to minus of tau max into sine of 2 alpha p. So on this, you can see that for every alpha p, your shear stress and normal stress is simply given by a point on the circle. So when alpha p is equal to 0, you can see this is the maximum value of the normal stress. So this is sigma max. Then this angle is not alpha p, but it should be 2 alpha p. So then if your alpha p becomes 45 degrees, so when you reach over here, then you can see that you will reach the maximum value minus of tau max over here. And then as you go on increasing this angle to alpha p, when alpha p is equal to 90, that means 2 alpha p is 180, then you will come to the minimum value of stress, which is sigma min. So this is the Morse circle. So each point gives, each point on the circle gives the normal stress, which is of course sigma x prime, and shear stress, so we are calling this as sigma and we are calling that as tau. So we get this sigma and tau for a given alpha p, where alpha p is the rotation relative to the principal axis. So this is you know, the graphical way of just visualizing how the stresses on that plane are changing. So now we have a pretty good understanding of what happens as if you look at any point in your whatever the material is, as you sort of change the plane on which you're calculating the stress is going to keep changing, and then you'll have some maximum stress, minimum stress, and so forth. But for frictional materials, and now is where the property of the particles and granular materials come in. The part above this is just general, it's true for everything, but the property of the granular material comes in here, which is the yield loci or the yield point, or the locus of the yield point. And for granular materials, the most common yield criterion that seems to work quite well is what is known as the Mohr-Coulomb yield criterion. Okay. And that essentially says that at the yield point, the shear stress at the yield point is equal to constant, I'm calling it as F prime, into the normal stress at that point. So here F prime, which sometimes we can write as tan of beta, is the coefficient of internal friction. So in a sense, we have gone from, let's say, when we have just two flat surfaces moving against each other, we had the frictional force is just equal to coefficient of friction, which is mu times the normal stress. We have now generalized that, and we are writing it in terms of stresses, which is force per unit area, because now you have a really complex material inside. And as soon as this condition is satisfied, then your material will yield. So now we have two things that we can, because if we plot this again on the same thing, then if I plot on the same sort of axes, tau y versus sigma, then this essentially gives us a straight line. And here I can put it as plus and minus, because it's just the magnitude that matters. So over here also I have this. So we have called this as tan of beta, so that means this angle could be written as beta, and this slope is just f prime. So this is a straight line of the yield stress versus sigma. So now we have two things. The stress actually goes always along the circle, and for a material to yield, you have to be on this line. So essentially, what we have to do is we have to combine this and this, and so what I will do then is we can essentially, should I just draw another one? I think that's probably better. So if we combine the two, not wasting any paper, I can keep writing more and more. So if we combine the Mohr circle with the yield criterion, then we will just get something like this, which is So let me draw the Mohr circle first. Sigma I am here. This is sigma, and this is both. I'm going to plot. I'm just writing it as tau, but it could be both tau and tau I. And from here, just at the point of yield, you will have this. And so this graph, so this is the Mohr circle. So it's just exactly at the point of yielding because it's tangent to the yield line. So this line is the yield line, that is the Mohr circle, and it is just about tangent. And we know that this angle is beta. So if we look at this, we see that since this is tangent, then obviously this is 90 degrees. So you have a right angle triangle over here. We know that the hypotenuse of the right angle triangle is sigma m, and we also know that the radius of this is tau max. So opposite side upon hypotenuse is sine of beta. So then from the geometry we can see that at the yield point we have, just from the geometry of this, that tau max divided by sigma m. Can we write it in terms of beta? Can someone tell me what will this be? What is tau max by sigma m?
Sine
If this
beta.
I have to keep asking questions, otherwise I never know if anyone is there. I think I always feel I'm talking only to the computer. So this is what you get. So this is the, if you have any material, now if we go back, what have we done so far? Well, we have managed to such a long journey. So we have started with this type of stress tensor. We have been able to express that stress tensor as just sigma and tau, which are in terms of the principal stresses and the angle alpha p, which is relative to the principal axis. And then once we put it in this form, we see that the stress it has to lie on this circle. And then this is the part, the Mohr-Coulomb criterion is the part which is the property of the granular material. And it says that, for the yield to occur, the shear stress must be some constant times the normal stress. So it's straight lines here. Then, so if we want this to fail, the two must be tangent, so you will get this. And of course, you can have a similar line here and you can see that it fails here also. So this is at the minus. That's why I said plus and minus. So this is the interesting thing, and we can easily find out also now that at what is the angle at which it fails, because this angle is alpha. Let's call this angle over here, let's call that as alpha s. So the failure will happen at plus and minus alpha s, which is the angle of the slip plane. So from here, this one we'll see that sigma max minus sigma min divided by is equal to sine beta, which also you can write as just the ratio of the so this is another way of writing the same thing. So at the point of yield, your ratio of sigma max to sigma min should be given by this. Obviously, if you have a situation like this, it can happen that this is my yield criterion, but this is my mode circle. What does this mean? This means that there is no yield. The material is far from the yield condition because this is the stress. The stress is really small and it doesn't actually touch the yield condition. So it's not going to yield. However, when you keep on increasing the stresses, the radius of that circle will go on increasing. So, the key thing, if you see this, if you want to increase the radius of the circle, that means your sigma max and sigma min have to become more and more different. If sigma max is equal to sigma min, then you see that tau max will simply be equal to 0. So if tau max is 0, that means the radius of the circle is 0, so it will never yield. So if your maximum principal normal stress and minimum normal stress, as they become large, as the difference between the two becomes larger, then the radius of the mode circle becomes larger and larger, and at some point it will yield. I should just mention that it's just not possible for something like this to happen, that the circle is going beyond the yield line. That doesn't happen is because as soon as it reaches, as soon as it sort of achieves this condition, as soon as the circle becomes tangent, the material will yield and the stresses will relax so that you can never cross this line. So you'll always be sort of within the envelope. So, very often we will call this ratio by the constant K, and we can show the yield condition in terms of this constant also by just plotting. I'll just call this as sigma 1 and sigma 2, which could be sigma max or sigma min. So if sigma 1 is sigma max, then you will have, this is the yield line. And if sigma 2 is sigma max, then this is the yield line. And this has a slope k. This has the slope 1 by k. And what you will have is that within this, okay, you have no yield because the two are quite close to each other, and over here the material will yield, over here the material will yield. So this is the thing, that we have to understand what the stress components are, and because the yield depends on both shear stress and normal stress, and the simple condition for yielding to occur is that the maximum to minimum principal normal stresses should be equal to K. If it is less than K, it will not yield. Okay. So with that, I will stop here. And some people had some problems downloading the codes that I had put on Moodle. I will put the correct things. I'll make the changes. But Niladri has put the codes, zip file for all the codes on teams, and you can have a look at them there. Okay, but I will fix what is wrong with Moodle also. Okay, so